Welcome to this ATA Insights webinar. Thank you for your ongoing interest and support of our webinar program. Today's session will begin in 2 minutes. ATA Insights Webinars is an online platform for the dissemination of professional renewable energy knowledge across international borders. Our aim is to democratize access to information, for innovation to spread faster, and to make the industry more competitive. And we do this through our online sessions, open to all our members. Every year, we do more than 100 sessions with over 250 speakers, 50,000 attendees from more than 50 countries. To participate in the session today, use the chat on the right-hand side to introduce yourself, your company, and where you're joining from. Under the screen, you will find the Q&A box, where you can send your questions for the speakers. We will get to as many as we can today. We're recording this session, and we will send you a link to the materials in a few days. Please consider supporting our content creation for the webinar program. Contact us on the email on screen.
Hello, everyone, and good afternoon, good evening, or good morning, depending on where you're connecting today. And welcome to this online session, Digital Solutions for Monitoring and Optimizing CSP and PV Plants. My name is Christina Galan from ATA Insights, and I will be the moderator for this session. I do have a couple of housekeeping rules to do first, then we will move on to the structure of the webinar. So first and foremost, this webinar is being recorded, and we will send everyone a link to the recording of the webinar and the presentation slides available, so approved by our speakers today. It will be sent in a couple of days, but in between this week and next week. If you are connecting on Zoom and you have any questions, you have there a Q&A box. So please, we will be having a Q&A session in the end and also in between presentations. So if you have any questions, feel free to use that space. I'm seeing that there's people already saying hi through the chat. Great. Yes, please, we do encourage people using the chat to introduce themselves, tell us where you're coming from, your job title, and why digital solutions for monitoring and optimizing CSP and PV plants are interesting for you. If you are connecting on YouTube, you also have a chat. So please, if you have any questions, send them our way, that we will be receiving them from our team. Without further ado, this webinar is going to last around approximately 2 hours. We will go through 4 different presentations. In the end, we will have a Q&A session. This webinar is sponsored by the German Aerospace Center, DLR. So we want to thank them for sponsoring, and thank you guys also for being the speakers today. We're really happy to have you here. So we're going to start with our first presentation. We have Alex Brenner. Alex Brenner, if you can come to the front and share your screen.
Yes. Okay.
Perfect. Alex Brenner is going to talk about loop-wise mass flow monitoring and parabolic through fields. I see your presentation. So Alex, thank you for being here. I know you're going to do a quick introduction of DLR, so the floor is yours.
Yes, thank you for the introduction. So I will be the first speaker, so I will quickly introduce the project where this webinar is based on. So it's the Außensol AI project, and we developed AI methods for autonomous and self-optimizing solar energy generation systems. And yeah, the project runtime was from 2022 until this year's November. And yeah, the project partners here were DLR, German Aerospace Center, CSP Services, the Technical University of Munich, Forschungszentrum Jülich, Fortis, which is another German research company, and we also had associated partners with us, Marquesado Solar and JTI. So the project was sponsored by the Federal Ministry for the Environment, Climate Action, Nature Conservation, and Nuclear Safety. And let me quickly give you an overview of the presentations. So I will start with the loop-wise mass flow monitoring in parabolic trough fields. My colleague Matthias Kuhl will then go on with the topic towards intelligent operation of CSP towers. Then Rafael will continue with the topic training of a machine learning model for processing airborne solar field images without labeled data. And then finally, Dr. Bijan Nouri will tell us something about generative AI for all-sky image-based solar nowcasting. So yeah, with this overview, I will start into the first topic, which is the loopwise mass flow monitoring in parabolic trough fields. So yeah, let me start with a quick motivation and an overview for you. So in a parabolic trough field, here we have an aerial view of a parabolic trough field. We typically have mass flow measurements at a subfield level, but we don't have mass flow measurements at each loop. Yeah, that's in some applications that's a problem because the loop mass flow would be also interesting. So for example, if we think of the first application where we need the loop flow is hydraulic balancing. So in these large parabolic trough fields, we somehow need to distribute the flow equally. And during an initial hydraulic balancing procedure, we want to achieve equal loop outlet temperatures under nominal conditions. So we can throttle valves at each loop and adjust the valve opening to reach this goal. And we can also adjust this during the operation. But for this, the knowledge of the actual loop flow is helpful. And to give you an impression of the how it looks like if the flow is not spread it equally. Here we have a simulation with 19 loops here. And if we do not have throttled loops here, then we see that the mass flow, yeah, it's in the first loop, it's way bigger than in the last loop, and therefore also the temperature is not equally distributed. So that's a big point in parabolic trough fields. The second application here is performance monitoring. So in parabolic trough fields, yeah, if you want to know the absolute value of the performance for each loop or for each collector, you need absolute values of the mass flow, of course. And if you don't have installed a measurement instrumentation there, then that's usually impossible. So you so far you need to attach additional measurement equipment here. But yeah, with our method, we can avoid that. So let me give you an overview of the measurement equipment, what we usually have available in a parabolic trough field and what we don't have. Let's start with that part. As I said before, we usually do not have mass flow measurements at each loop. Yeah, so we only have measurements at certain positions in the field. In the case of a parabolic trough field, we have loop we have mass flow measurements at the subfield inland. And if you want to retrofit it, this is often very expensive because you have to yeah, open the pipe, attach measurement instrumentation, and then you have to connect it to the data acquisition system. So this is yeah, expensive, sometimes not possible, and you would need a lot of instruments here. So what we use for our approach is we use the temperature sensors, which are already installed at the parabolic trough collectors. And what we also use is the ability of the collectors to change the heat input. So by adjusting the focus, we can change the heat input to the heat transfer fluid, and therefore we can also adjust the temperature of the heat temperature fluid. And that's our main benefit for our approach. So yeah, our idea in this approach is, we are using the temperature gradients, and we are using this as a tracer to determine the fluid flow. But with this approach, there's also a challenge with that, because you always have thermal interaction between the pipe material and the fluid. And this thermal interaction, it shifts the fluid runtime and the runtime of the temperature signal. So you somehow need a correction to account for that. And to give you an idea of this challenge, the plot here on the right side, it shows a simulation where we defocused the first collector in the loop. And then you see the temperature drop is also measured at the other collectors with a short time delay. And we call this the temperature runtime here. And what you also see in this plot is we have simulated this for a regular steel pipe, for a typical absorber tube. And we also have done the simulation for a low heat capacity material. And in this case, you see that the temperature drop, it's shifted, so it's not 100% the same as the fluid runtime. So you need this correction. Okay, so the main goal of this temperature gradients is, we want to have a clearly recognizable temperature signal. So what we did here is we defocused the first collector, and then you see the temperature gradient flowing through the loop. And we can measure this gradient at the following sensors. We can also do a repeating signal, so that's also possible. So this all helps for the measurement uncertainty. So what we did in this study is a proof of concept study, and we validated it with test data from the Andersol 3 power plant. So one more slide about the approach. Because our way to solve this challenge of the thermal interaction with the pipe was using transient simulations as a basis for this correction function. So the idea was, okay, the correction function, it should fit for various pipe materials, for various processes and geometric properties. We did transient simulations, and we were varying all these parameters. We were also using different heat transfer fluids, thermal oil and solar salt. And what the correction function does, it summarizes all these simulation results, all these thousands of different simulations, and it solves the inverse problem. And the inverse problem is, we are using the temperature signal, the runtime of the temperature, and with this input, we can calculate the fluid runtime. So the runtime of the temperature signal, that's our measurement input in this case. And we put this in our correction function, and then we can get the actual fluid runtime. And one more important thing here is there are other approaches out there which use a similar idea of this time of flight method, but with our method, we can calculate absolute values of the fluid runtime, and I think that's a big benefit here. So let's have a look at the validation results from the measurements from the Andersol 3 plant. So we had multiple defocusing measurements here available to give an overview of the validation setup. It was 12 experiments with 38 collectors and 456 defocusing procedures, so a lot of validation data here. And we used, in this case, the runtime between the collector 3 and 4 in a loop. And we also see the temperature signals here on the right side. This is for one defocusing procedure. In this case, we see 3 defocusing procedures. So you see the temperature drops first on collector 1, which is defocused, and then you see with the time difference also the temperature drop at collector. So I can show you this at collector 2, 3, 4, and also here is another procedure, and here is another one. So what we also have in this slide is the outlet temperature of the subfield, which was also important for us to monitor. We use here the mass flow as a comparison because this also compensates for density changes. So let's come to the results. We compared, as I said before, the mass flow from the subfield flow meter with our defocusing procedure. So and the plot on the bar plot here on the right, we see the flow meter in orange and our defocusing procedure in blue. And the overall data showed us that our defocusing procedure, it systematically underestimated the mass flow by approximately 6%. So we can also take this into account and correct this, and then we end up with a mean absolute percentage error of 1.7% from our method compared to the regular flow meter installations. What we also have to account in this validation study, the subfield flow meters, they were just standard industrial flow meters, so they have an uncertainty as well. So this is also has to be said for this validation. Another outcome of this study was, we also looked at the impact on the plant operation, because you don't want to, somehow impact the plant operation negatively. So we looked at the decrease of the solar yield. So if you're defocusing every loop every 30 minutes, then a rough estimate is, there's a decrease in the solar yield of less than 1.25%. And we also looked at the influence on the outlet temperature due to the collector defocusing, and we saw that this is very small. So in the plot on the right side, you see it's only 2 Kelvin within 5 minutes, so very small influence here. So another impact is a temperature change due to simultaneous defocusing. Because this simultaneous defocusing, it leads to a contraction of the fluid and then to a change in the fluid velocity, and therefore the temperature increases by 9 Kelvin here. But you can also prevent this if you have a short time delay between the defocusing procedures, so you can also minimize this effect. So let's come to a summary and an outlook of this procedure. So most important for our approach is we do not need additional hardware for the mass flow measurement. So it's a low-cost flow measurement here. We saw that in this validation study, the error compared to the flow meter of the Andasol 3 power plant was about 6%. And we also have more details about this procedure and also this validation study in the paper, which is currently under review. But if you're interested, you will find this hopefully in a few weeks. What we need for further investigations is calibrated instrumentation. So we will have this as an outlook, and our next step will also to develop this method also for asymmetric solar field layouts, especially for process heat plants. I think this could be an interesting approach, and we also want to test this in a process heat plant during the next year. Okay, so that was my last slide. Thank you for your attention. And if you have any questions, feel free to ask.
Okay, Alex. Well, thank you so much for this first presentation and introducing us to the Alcesol AI project. I don't see any questions in the moment, but we do have a couple of pre-prepared questions. However, since we will have a Q&A session at the end, feel free to put anyone your questions in the Q&A box at any time. I see, Thomas, that you do have a question, but it's in the chat. I see it now, but however, for future questions, please put it in the Q&A box so we just don't miss it. So Alex, here's a question from Thomas. He says, where do you see the biggest issues with the calibration?
Okay, yeah. So with the calibration, so what we didn't had so far is really a freshly calibrated mass flow meters in each loop, and that's something which is still missing. And you need, of course, this calibration also for high temperatures for up to 400 degrees. And so that's still something which we need to do. And yeah, this was also the validation so far was only for thermal oil. And if we also want to apply this procedure for solar salt, of course, then you also need different instruments, and this is still a challenge for solar salt at this high temperatures, I would say. Yeah.
Okay, perfect. Thank you. Alex, next question. What is the difference to an approach which only calculates the relative flow distribution in a parabolic throw subfield?
Yeah, so as I showed here, the validation study, it was for a typical parabolic trough field. Here, if you just want to get values for the hydraulic balancing, the relative flow, that's completely sufficient. You don't need to have these absolute values. But if you think of a different application, for example, in chemical process engineering, the layout of the plant, it's completely different. You don't have parallel loops, and there you really need absolute values. So that's the main advantage here. If you can get absolute values, then you don't need to rely on another measurement instrument, which gives you the absolute value. Yeah.
Okay, perfect. Well, thank you for that. Next question I have, how often do you need to run the transient simulations to determine the correction function?
Okay, so for if the setup, the layout stays the same, then you only need to run this one time. So that's also a big advantage. So you don't need to repeatedly calculate it with the transient simulations. So it's only done once. But if you change the setup completely, for example, different plant, different pipe material, then of course you have to redo the transient simulations. Yeah, but we will. We can hopefully validate this in our next study in the process heat plant, where we have a completely different layout, and we also want to check, how many simulations do we need additionally to the other setup we had before.
Okay, perfect. Well, thank you. Alex, if it's okay, I can ask you just one last question that Thomas left, and we can move on to Matthias's presentation. So Thomas asks, have you considered transient mass flows in your simulations or validations with andesol plant data?
We have not with andesol data, only with simulations. Yeah, here we have considered like an increasing mass flow, decreasing mass flow, and what we have seen from this simulation study is that with this method, we are pretty much at the average mass flow during this measurement time. And the average is, the measurement time is also, given by the fluid running through the pipe, of course. So we saw that it's pretty close to the average. If you have increasing or decreasing mass flows.
All right. Well, Alex, thank you so much for your presentation. We're going to move on to the next presentation. But however, please remember that we do have more space for Q&As after. So Matthias, whenever you're ready, you can share your slides. Matthias's title is Towards Intelligent CSP Tower Operation, AI, collaboration, and data-driven control infrastructure. So there, it's easier if I read it from there. So Matthias, thank you for being here. And whenever you're ready, you can start.
Yeah, thank you for the short introduction. And hello, everyone. My name is Matthias Kuhl from the DLR Institute of Solar Research, and I'm excited to present you our work on making concentrated solar power towers more intelligent and efficient through AI-based and data-driven modeling and control. In this presentation, I will show you how we can use machine learning to build digital twins of plant components and integrate them into optimal control concept. However, in this presentation, I will only be able to give you a quick overview of all of the topics we are working on. Due to the time, I won't be able to go too much into the detail about the methods, but the corresponding publications are linked. So first of all, let's start with a short motivation why we need those intelligent methods. Concentrated solar power towers are extremely complex systems. We are dealing with thousands of heliostats that have to track and align precisely, and a large thermal receiver that is constantly exposed to changing solar conditions. This means we have to solve many coupled control tasks. And to handle this complexity efficiently, we can use data-driven models that act as digital twins of the plant components and integrate those models into model predictive control so that our system can operate proactively and adapt in real time. The results are higher efficiencies, more stable operation, and lower operational costs, both for existing and also future installations of CSP towers. In my presentation, we will focus on two different data-driven digital twins. The first one is the optical model, which represents the heliostat field. It simulates the flux density distribution of individual heliostats on the receiver and uses aim points as control input. The goal is to achieve a flux distribution that is optimized for thermal efficiency of the receiver and also to minimize spillage. With optical models, we can then perform automatic and optimized aim point control to achieve those goals. The second model is the thermal digital twin of the receiver. It describes the thermal behavior of the receiver and uses the mass flow rate as control input. The objective here is to maintain a constant outlet temperature, which is essential for the downstream processes such as the steam cycle or the storage charging. And we can achieve this constant temperature by reacting predictively to solar fluctuations. And the model helps to avoid thermal stress, overshooting of the temperature, and therefore material damage. Together, those two models form the foundation for predictive and data-driven control of the CSP plant. So let's move on to the first part, the optical models, or the heliostat field. The optical models of heliostats are further composed of two different parts. The first one is the alignment model, which determines the required actuator motor position for the desired aim point. Here, the goal is to track precisely on the desired aim point on the receiver, and usually such alignment models are represented by rigid body models. The second optical model of a heliostat is the flux model, which predicts the flux distribution around the aim point for a single heliostat. And the flux model is usually represented by convolutional models, ray tracers, or by more recent approaches directly by neural networks. In our case, both models are trained on data from the camera target method, which provides target images which show isolated focus spots of individual heliostats, which are measurements conducted routinely during the year. So we have a lot of data available from this automated calibration process. So we start with the alignment model, how we improved this part of the heliostats. We have two complementary approaches. So first, we improved the kinematic model itself by extending the classic rigid body model of the heliostat with a neural network-based parameter estimator. This allows the system to automatically learn and correct for small deviations in those parameters based on ambient conditions, which the original kinematic model couldn't account for. The second enhancement we made is that we enhanced the image processing pipeline because we found that especially shading and blocking and also image noise in those target images heavily affect the accuracy of the downstream calibration process. Therefore, we use an AI-based centroid detection approach, which is robust to those influences. Just shortly, a few results. For the improved kinematic model, we could see that our hybrid approach with the neural network-based estimator was always more accurate than the state-of-the-art method. And for the image processing pipeline, we could see that by our approach, we could account for those error sources mentioned earlier, like shading and blocking. To summarize both of this, we could improve the pointing accuracy from 2 millirads to around 1 millirad, and soon we are approaching 0.5 millirads. This pointing accuracy directly translates to higher optical efficiencies due to reduced spillage and more precise flux control on the receiver. And we could do all this by just adjusting the calibration algorithms, so we didn't need any hardware changes to achieve those. So let's move on to the flux models. The goal was to predict flux densities for heliostats on the receiver solely by using those calibration images. We have developed different approaches to achieve this. One approach is to use a neural network directly to predict focus spots based on target images, or a different approach where we use those target images to predict heliostat surfaces as an intermediate stat, which can then be used in a ray tracer. Compared to conventional characterization techniques like deflectometry or photogrammetry, this approach comes with minimal effort because we use the calibration images which are available anyway and can be done automatically. Here shortly some results. So we compared the two data-driven approaches, which are the two colors here, to current state-of-the-art methods like deflectometry, a convolutional approach, or the ideal heliostat assumption. And we can see that our data-driven approach achieves lower errors for all heliostats. So after explaining the alignment model and the flux model, now we have a look at how we can integrate this in the power plant control. So once the models are trained, we can integrate them into an aimpoint optimizer that automatically controls the heliostat field. The control interface receives the current heliostat field state and initializes the optical models for all heliostats. And then based on a desired target flux density, which is optimized for thermal efficiency of the receiver, the optimizer computes the optimal aim points, which best reproduce this target flux density with the available heliostats. The number of active heliostats can then be set either manually via the user interface or automatically by an external controller. As an example, we also integrated this aimpoint optimizer in our autonomous CSP operation software, which then automatically controls the whole plant, including the heliostat field. At the solar tower in Jülich, we demonstrated this system in real operation. The optimization runs every 20 minutes to update for cosine efficiencies and shading and blocking, and with a computation time of 10 seconds per cycle. The results show very uniform receiver temperature profiles, reduced spillage, and higher thermal efficiencies. So let's move on to the next part, the thermal models of the receiver. So one of the main challenges in solar tower operation is dealing with fast DNI fluctuations, for example, when clouds pass over the field. To handle this, we use model predictive control to anticipate these changes before they happen and adjust the mass flow proactively. This allows the system to keep the outlet temperature stable, even under dynamic solar conditions. However, such predictive control requires accurate thermal models that describe the receiver dynamics, and in our case, we use data-driven models to do so. To build an accurate thermal model of the receiver, we used real operational data recorded directly at the solar tower in Jülich. During live operation, we continuously collected a wide range of measurements, like temperatures at the in and outlets, mass flow measurements, infrared cameras that show the surface temperatures, flux density cameras that show or measure the reflected solar flux from the receiver. And we also need DNI nowcasting so that the model can anticipate changes in the incoming solar radiation. All of this data is then used to train a transformer model to learn the thermal dynamics of the receiver directly from measurements. This thermal model is then, after training, included in the mass flow control software at the solar tower in Jülich. The system continuously collects the live data from the plant, including all of the data mentioned before, and feeds this into the transformer model in real time. The entire setup has been fully implemented and tested in live operation at the solar tower in Jülich, proving the feasibility of such a data-driven predictive control approach. However, the performance evaluation is still ongoing as part of an ongoing PhD project, but initial results already show that this method provides better stability. So I'm looking at the time, so I will conclude fast. So we developed two digital twins of the key components, the heliostat field and the receiver. Both systems were implemented and demonstrated at the solar tower in Jülich and showed great potential. The outlook and goal would be that we would like to transfer this methodology to commercial scale CSP plants or test it at different facilities. So if you're interested in cooperation or test it at your facilities, feel free to reach out to me. So with this, thank you for your attention.
Well, thank you, Matthias. Thank you for your presentation. So we do have a question for you. So I'm going to go with it. It's a bit long, so if you need any repetition, just let me know. In the results for the heliostat pointing accuracy, it looked like the accuracy of the hybrid method increases at a very small rate, but still increases as more training data is added. Can you elaborate on this effect? Does it have to do with the training data input to the model?
Yes.
Do you want me to repeat?
So, no, it's okay.
Okay,
I got
you got
everything.
it.
Thank you for your question. So I think you mean that here we can see with increasing training data set size, we can see that the pointing accuracy gets worse a little bit. This we wouldn't expect this because usually more data means that our model would get more accurate. In this particular test case, we found out that it was the data set itself. So usually the very important for the training of such a model is that the data set is balanced really good so that the calibration data is distributed equally across all sun positions. In this data set, we found that this wasn't the case for the training data set if we increased it to 300 samples. So the reason why the pointing accuracy gets worse for the higher data training samples is that the data set wasn't balanced enough. So we could counteract with different measures to avoid this, but there was a different publication on the dataset sampling. So I hope I could answer your question.
Okay, Matthias, well, thank you for that. And thank you, Luca, for your question. If you do need a bit more of explanation, you can still use the Q&A question box, because we will have later a session. So Matthias, if that's okay, I'll go to the next presentation and then we will go back again with the Q&A. So Rafael, whenever
Yes,
you're
good.
ready.
Thank you.
Thank you. Thank you for your presentation. Whenever you're ready, Rafael, you can start sharing your screen. Great. So here we are with the presentation on training of a machine learning model for processing airborne solar field images without labeled data. So I see your screen perfectly. We see you great. So whenever you're ready.
Great. All right. So thanks for the introduction, Christina, and thank you everyone for joining today's session. My name is Rafael Brother, and I'm currently pursuing my PhD at the DLR Institute of Solar Research in the condition monitoring group. And today I will show you our work on developing deep learning models using only synthetic image data. All right. So, oops. Yeah. First, let's start with what condition monitoring is and why it's important. So in concentrated solar thermal plants, especially those using heliostats, regular inspection are essential to ensure efficient and safe operation. And key parameters here include collector orientation, soiling, and surface, amongst others. And because these heliostat fields cover such large areas, drone-based inspection methods have become popular for performing this task and scanning the site. However, a major bottleneck lies in image processing here, because most existing methods use conventional algorithms and rely on accurately detecting specific features, such as the mirror corners of the heliostat collectors, as can be seen here, and this with sub-pixel accuracy. And this detection basically is the basis for most downstream tasks, which I have mentioned before, and we will deal with exactly this problem today. Because detecting these features is particularly challenging due to occlusions, for example, reflections, and usually these methods require search windows which are processed iteratively, making it slow. And these search windows also depend on prior knowledge of the field and camera pose. And as a result, these methods often lack the accuracy, robustness, and speed which is needed for practical application. This is where deep learning steps in, as it has proven highly effective in overcoming exactly such limitations across many domains, as we all know. Yet in solar field inspection, a key challenge remains. Deep learning requires large labeled data sets, which are typically not available, or if available, expensive to create manually. And our approach to address this challenge is using synthetic training data for model development. So how do we do this? To generate our synthetic data, we use Blender along with several extensions, and this lets us create detailed 3D scenes. We use a parametric heliostat model, which is shown here, which allows us to easily modify its geometry, and we can add other objects shown here, and this results in a scene like here, which is very diverse and lifelike. And once the scene is set up, we render photorealistic, high-resolution images. And because we know the exact position of every object in the scene, we can automatically generate perfect labels for training our deep learning models. And this is shown here in this image on the lower right. And now we have a problem, because although our synthetic images look very convincing to the human eye, they still differ from real-world images, which is subtle but in very important ways. And these differences reduce model performance when transferring a model from simulation to reality. And this challenge is known the sim-to-real gap. And to address this, we refined our scene generation process and systematically evaluated performance on real data. And in our study, we showed that using realistic procedural ground textures, distractor objects like trees or containers, fences, random positioning, shown here, everything is shuffled, and realistic heliostat orientations yields the best results and is the best scenario for minimizing the sim-to-real gap. And overall, in this study, we found that synthetic training performs pretty well, because our model accurately detected over 60% of heliostat mirror corners in real-world images. And I'm not going into more detail here, but refer to this study, which is already published in Solar Energy, so you can look into it. Now, there's another challenge, because to deploy our trained models in real applications, we also need to account for different heliostat geometries. Heliostat can vary in both facet number and mirror area, and here is a typical rectangular heliostat with a middle gap. And in the literature, we then identified that there are at least 33 distinct geometries which are used in research or commercial plans. This is to different applications or development which is going on. And now, fortunately, our parametric heliostat model can automatically replicate any rectangular geometry. And this allows us to render new data sets and train models tailored to each specific design. Now, the next question we answered here is whether there is a more efficient way to adapt the model, if there's already one available, or if there's even a single model that can cover all cases. And these findings are discussed in detail in our upcoming journal publication, which will be called Geometry Transfer of Deep Neural Networks for Heliostat Detection. So now that we have an idea on how to address the sim-to-real gap and how our approach adapts to different heliostat geometries, let's take a closer look at the deep learning model we used itself. So we employ a one-stage encoder-decoder architecture, which is shown here. And with a single image forward pass, the model predicts two heat maps, one for object positions and another for feature positions. And simultaneously, the model regresses different parameters such as bounding box size and subpixel location of features. And this makes the model very simple, very fast, and very versatile, because we can just add additional heads to do more tasks, for example, classification of damages. Now, once we have the model outputs, we then perform an automated post-processing which refines them. This way we get, here from the raw model predictions, we get consistent, accurate, and identified detection. Identified means we know which heliostat is visible in this image and which corner a detected feature corresponds to. And with this, we obtain all the necessary information for most downstream tasks. And now let's look at how this approach performs in comparison to our so far state-of-the-art conventional image processing algorithm. So, and to evaluate these two approaches, we conduct several drone flights over our heliostat field at the Solar Tower Jülich plant. And for the test case shown here, we selected a particularly challenging flight, which was captured at a height of 30 meters with a gimbal pitch angle of 45 degrees. And this results in strong occlusions, many heliostats visible per frame, reflections, which in general makes it a realistic but demanding scenario. And from this meander flight, which is shown here, we selected 5 representative images and manually labeled all features, as you can see here. And we use these features to evaluate how well our methods detect heliostat features under real-world conditions. First, let's take a look at detection rates. So, as mentioned earlier, the conventional method relies on search windows, which is why we evaluate 2 conditions. The first one is the ideal scenario shown here, where we assume perfect camera poses and accurate knowledge of the field and heliostat orientations. So with this knowledge, we can perfectly place search windows, which basically already almost detect the features. And the second case is the real measurement, in which we typically don't have such information because the camera pose is prone to noise and the heliostat orientation may be known, but can also be different than assumed if it's an outlier. And this leads to a less accurate placement of search windows, which is shown here in the image below. And now to evaluate the detection performance, we use 2 metrics, precision and recall. Precision basically tells us how many of the model's predictions are correct, so essentially how many false positives we get. And recall measures how many of the ground truth features we actually detect. And we want to maximize both, obviously, because we want to get as many features, but as little positives, false positives as possible. Now we look at 2 cases. The first one is pure detection, where a prediction counts as correct if it is within 3 pixels of a ground truth feature, as shown here. So if we lie on this diameter, we are fine. Otherwise, it is counted as false positive, and then the precision is calculated respectively. And the second case is detection and identification, which is basically the same, but the prediction additionally must have the correct corner ID and be assigned to the correct heliostat. So a more strict precision metric. And here are the results. And if we go from left to right, we can see in the ideal scenario, the conventional method reaches about 92% precision and detects 80% of all features. We can see that with identification, the results are the same because the IDs come directly from the well-placed search windows. And we can also see that processing per image takes around 31.6 seconds. Now, if we use, in the ideal case, if we use the search windows and basically use them to match our raw model detections, we can see that we can outperform already the conventional image processing algorithm. We have a higher precision, higher recall, and a significantly lower processing time. And yeah, now let's move on to the real measurement. And in the real measurement, the difference becomes even more pronounced. We can see that the conventional method fails completely, as you can see here. Regarding the metrics, it detects no features at all, but delivers a high number of false positives. And this is because the search windows are not placed correctly. The AI model, on the other hand, which does not rely on search windows, still achieves 97% precision, so the highest, and detects 75% of all features, which is comparable to the conventional method under ideal conditions. But we can also see when we consider identification that around about 25% of the detections are not identified correctly. And this, in the end, means that we can use roughly 60% of the features for downstream tasks where we know they are correctly detected and identified. And this is sufficient for most downstream tasks and, of course, very strong compared to the conventional method in the real measurement, as you can see. Now let's zoom in on the detected feature itself and how accurate they actually are. So we consider all features marked as true positives. And as mentioned earlier, we need subpixel accuracy to make the downstream processing reliable. And in the plots, you can see the pixel deviations in the X and Y directions for both the conventional and the AI-based method. And here we can clearly see that the AI model is much more stable, showing far less noise, and that both methods have a small positive shift in the right direction. But overall, the AI model shows a significantly lower standard deviation of around 0.5 pixels, which confirms subpixel accuracy. However, we also have to note here that part of these small deviations can also be attributed to manual labeling. So the error of 0.5 pixels is a, I would say, good guess, because manual labeling also introduces additional uncertainty. And we could see this partly here because it's not always easy to match the correct corner. To sum it up, overall, we see that we achieve very high detection rates and high positional accuracy here. All right, to conclude, so on a system level, we have seen that our deep learning model clearly outperforms the conventional state-of-the-art approach, both when integrated with search windows and even more notably in the real measurement. And these results demonstrate the potential of deep learning to enhance and, of course, automate heliostat condition monitoring tasks. But we also have seen that correct identification still offers potential for improvement here. And we will address this in the future. And more broadly, we have also demonstrated that synthetic data can effectively train AI models, and even under challenging conditions such as reflections, repetitive structures, high resolution imagery. And this approach directly tackles the issue of limited real-world data and shows strong potential for transfer to other domains, of course. And to just mention a few examples, here, of course, PV plant monitoring would be very close, but of course, also building inspection, especially for modern glass facades, which will also come with reflections. Automated waste recycling, where diverse object detection may also be essential, as we have many high diversity of different objects. And even more specialized applications, such as wildlife monitoring from airborne images, shown here, could benefit from synthetic data because it can improve the detection of rare species and help to balance class distributions. Here are the references. And this brings us to the end of the presentation. Here you can see my contact details. I would like to thank you very much for your attention, and I'm happy to answer your questions.
Thank you, Rafael, for your presentation. Just a reminder to everyone, we will share these slides with everyone in a couple of days. So no worries, you don't need to write everything down because that would be quite difficult. Rafael, a quick question for you before we move on to the next presentation. How much time is required to generate data and train a model?
Okay, so currently with our current setup, and we use a HPC cluster, we require around 6 hours to render a data set for a new geometry, and then roughly 20 minutes to train a model. But we're also working on approaches how to speed up the training, especially. So I would say roughly a day currently, with potential to significantly improve, of course.
Okay, so this might change in the
Yes.
near future. All right. Well, Rafael, thank you so much for your presentation. Next presentation will be from Dr. Bijan Nouri. Bijan, thank you for being here today. Bijan, whenever you're ready, you can start sharing your slides. The title is Cutting Edge Generative AI for Intra-Hour Solar Forecasting. So thank you so much for being with us today. And I see that you are sharing your slide. There you go. Perfect.
Okay.
Well, the floor is yours.
Thank you. Thank you for the for the introduction. Just to mention at the start, so I will present the work of my colleague Jan Fabel, which was the main researcher on this topic, but he was not available today. So here we can see the agenda of the presentation. I start with the motivation and the introduction. Then I will talk a little bit about generative forecasting approaches, also a little bit on ramp event prediction, and we will follow or finalize it with a conclusion and outlook. So let's begin with the motivation. So why solar forecasting? Of course, we want to predict the expected energy yield of solar power plants. And we also want to anticipate local short-term fluctuations caused by clouds. Such fluctuations can be seen here on the right-hand side, or you can imagine that the irradiance will fluctuate depending whether or not the shadow will hit the ground or it will be a sunny patch. And of course, such ramp events can produce challenges. So the local power output will be variable, and this can have potential risks in terms of grid instabilities, or especially for higher solar penetrations. So what could be the benefit of intra-hour forecasting? For sure, we can increase or improve the situational awareness of plant and grid operators. We might be able to reduce storage requirements. We might improve market trading strategies, and especially in terms of CST, we could also optimize the control of the systems. What are the requirements? Well, depending on the forecast horizon and the spatial and temporal resolution needed, there are different technologies available. And if you really want to detect such local ramps, then we need local observations. So these can be sky cameras, like in our case, but also radiometers and other local measurements. Other options, if you want to look further into the future, but with a lower resolution, would be satellite data or NWP data. Then we are specifically interested in ramp events. So what is a ramp event? So commonly forecasting metrics are RMSE, MIE, and MBE, and these are interesting and good metrics if you want to evaluate the average accuracy of a system. So it's a good measure to assess the expected energy yield. However, it does not give you too much information on the variability within the forecast itself. So that's why we introduce a quite simple ramp event metrics. Basically, we have a threshold. This can be a threshold in terms of GHI, DNI, or GTI, depending on the application. And we look whether or not we have a ramp where the amplitude surpasses this certain threshold within a certain time window. So it is quite simple. And now let's talk a little bit on why we think we generative models could be a benefit, because the state of the art in forecasting is not based on generative models. These are normally or currently direct data-driven models, and they are optimized on RMSE. What do I mean with a direct data-driven direct model? So we have our input. These are sky images, and this can also be some meteorological time series. So this can be DNI data, GHI data, and so on. Then we have a model. So in our case, in our model, this is a vision transform and a time series transform, but this can also be a CNN or whatever other architecture you want to use. And this model will evaluate the data you give it, and then it will produce directly a multi-step forecast. And everything is done in a single step. So we train the model also end to end. And then these models are also evaluated with these standard metrics like RMSE, MI, MBE, and the corresponding forecast skill calculated by RMSE or MI. And they're really strong in terms of performance on these standard error metrics. However, they're really unsuitable to detect ramps itself, which we will show in later slides. And I mean, the best measure to see how good they perform in the traditional metrics is basically the skill score. So you can see that here we have a positive skill score. So that means that this data-driven model surpasses a baseline model, which is most often a persistence model. Now's the question. So when we know that these models are not that good in detecting ramps, how can we circumvent these issues in these approaches? So especially the main reason here are basically smoothed forecast curves based off the optimization on RMSE. And we think that generative forecasting approaches could be a solution. Here we have a different model architecture. So we start with a video prediction model. So we have our sky images, which take again images of the sky. And we have a given sequence of m pass images. And we will pass these images to our video prediction model. And the video prediction model will now create a forecast of synthetic potential future sky scenarios. So we get again sky images, but these are synthetic images, and they should represent the future. And we are not just creating a single scenario, we can create multiple scenarios for the same forecast horizon. So for each lead time, we can have 4, 8, or 12 different scenarios. Here the limitations is basically only computation. So that means we have also some probabilistic information, which is a measure for the uncertainty. And then this model has to be followed with a regressor or classifier. So we have a second model, which is used to derive the desired target quantity. This model is trained separately on real images, and then it is applied on the synthetic images during inference. And this model can predict, for example, ramp events directly, or also irradiance like GHI or DNI, or it could also detect or predict the cloud coverage. So now let's talk a little bit about training and testing these generative models. We trained 3 different generative models, and we tested them, of course, also. One model is the Sky GPT. This is a published model, so you can go to GitHub and you can get the source code of it. And it is basically an adaptation of the well-known video GPT model, and it uses also the 5 cells model. Then what we developed by ourselves, or what we did, is we have this DIT. This is an adaptation of the diffusion-based transformer model. And then also there's the FAR. So this is an adaptation of the frame auto-regression model. So this is a quite recent model, or the source code for this architecture was published, I think this year in spring. And we trained then such a model with our data. And for the training, we use data from the Plataforma Solar de Almería. So this is the PSA, which is operated by CIEMAT. And we use quite large data sets of the PSA to train these models. For the Sky GPT model, I have to mention that we trained the model based on the same hyperparameters configuration as given by the original publication. That's why this is the only model with a lower spatial resolution of 64 × 64 pixels compared to the other 2 models. And then, of course, we had to test the system. For the testing, we used a well-known benchmark dataset, which is also based on the PSA in Spain. These are 28 days, which were selected because they represent quite diverse sky conditions. So they are quite interesting in terms of forecasting tasks. And we created for each of these generative models 4 samples per lead time. And here we can see some quantitative results. So this is a really simple day. It's a clear sky day. The top row are the real data. Then it is followed by the 3 generative models, so the DIT, the FAR, and the SkyGPT. And each column is a different lead time. So basically the forecast horizon. So we look into the future from 1 minute up to 15 minutes. And we can see for this really simple conditions, the DIT and the FAR model, they can handle it quite well, but SkyGPT has some issues. So there's a lot of hallucination going on. So it predicts some clouds which don't exist. Next, let's have a look in a somewhat more complex scenario. So here we have quite a lot of clouds, but then we can also see that the cloud cover is breaking up. And we can see that the DIT and the FAR and also to a certain extent the SkyGPT can get some realistic sky scenarios. Of course, SkyGPT is a little bit more blurred, but this is mainly due to the lower spatial resolution. But now, especially here in the FAR, you can see the structures look quite realistic. However, for the larger focus horizons, for example, here in the FAR model, again, we can see we detected a lot more sky or free sky patches compared to the reality. So depending on the focus horizon, the uncertainties can be quite high. But the good thing, of course, is here, as I said, we are creating probabilistic results. So we have multiple samples for the same potential time in the future. So now let's have a look at the quantitative results. We start with the evaluation of the synthetic images itself and not on the downstream task. And here we used 3 error metrics. So we started with the MIA, so it's just the average error per pixel. Then the peak signal to noise ratio. So this is, I think, the most common metric in these generative or in these generative image models. So it is basically the ratio of the maximum possible signal to error, and it is given in decibels. And then there's the structural similarity indexes, which is also quite common error metrics in these tasks, which is a measure for perceptual similarity. So these 2 error metrics are, the model is better when the number is higher, basically. And what we can see for all 3 error metrics is that the DIT is outperforming the other 2 approaches. The FAR model is also outperforming the SkyGPT model, at least for most of the forecast horizons and for most of the error metrics. But it is clear that in terms of the synthetic images by itself, is that the DIT is outperforming the other ones quite clearly. And until now, the DIT is also the only model which we trained, which goes up to 30 minutes into the future. The other 2 models are only trained for forecast horizons up to 15 minutes ahead. Okay, now next, let's look into the downstream task. We wanted to detect ramp events. So for that, we trained the ramp classifier. This is a CNN model, and it was trained on real images, but then evaluated on synthetic images, which were generated by the generative models. And the ramp classifier just will predict whether or not there will be a ramp or no ramp. Additionally, we also introduced a baseline model, which is a really simple ramp persistence model. So we don't need the sky images. And if in the past some ramps were observed, then we predict also ramps. And this is also somewhat visualized here in this graphic. So it is a really dumb persistence model. So you should be able to beat this. Otherwise, something is going wrong. So let's evaluate this. Here we use quite traditional error metrics like the accuracy, precision, recall, and the F1 score. And here we have the results. And we added also the state-of-the-art data-driven model here in green. So this was this end-to-end model, which we showed at the beginning, which is quite performant when we are looking into these traditional error metrics. But what we can see is that it does perform quite well in terms of accuracy. This is just because it does not detect any ramps, which we can see in F1 score. And the reason why it is good in accuracy is because in most cases, there are no ramps. So we have almost no false positives. So accuracy is high, yay. But the F1 score is at 0. So we are not detecting any ramps at all. So it's basically unsuited. So we can predict the energy yield, but not the ramps. But the generative models, they are outperforming quite clearly the state-of-the-art model. And again, the DIT model seems to be the strongest. Only in terms of recall, we can see that the farm model is outperforming slightly the DIT. So to conclude, low RMSE does not guarantee realistic representations of the irradiance. And this is really an important fact because the RMSE is the standard error matrix for almost all forecast applications. Then we have seen that these generative models, which are quite capable in modeling cloud dynamics, and they offer a promising alternative to capture short-term variabilities. And we have also seen that these current video prediction models for all-sky imagers do still struggle for longer horizons. However, they are outperforming clearly the state-of-the-art when it comes to ramp rate prediction. And then he also has an outlook. So what can we do to improve these models? So one thing during training, we should focus on the highly variable cloud conditions. So often in our data, in our training data sets, we have a lot of clear sky scenarios or overcast scenarios where you don't have these high variabilities. So that could be one important feature. And leverage advances in generative video modeling. So this whole field is just evolving extremely fast. And we would also like to combine multiple perspectives to learn better cloud representation. So if you have multiple cameras or maybe even perspectives from other sensors like satellite data. Here we can see some of our references. And yeah, that's basically all from my side for now.
Perfect. Well, thank you, Bijan, for your presentation and going through your work. And also Jan, Jan Pavel, who couldn't attend today. Well, thank you so much. A question for you. What are the requirements for training and interference of the models?
Yeah, so for training, so for computation requirements, in this case, the generative models are quite hungry, so especially the DIT. So it was trained on a larger DLR HPC cluster, and I think we used 4 GPUs, these NVIDIA A100s with 80 gig RAM, and it trained maybe around 2 to 3 weeks. And then in terms of inference, the requirements are quite lower. So here it might be suffice to have a single GPU with 16 gig RAM, and then depending on how it really depends on inference, how many samples you want to generate, and so how many different scenarios per lead time, but it is real time capable.
Okay, perfect. Well, thank you so much for your question. Here we have another one from Ignacio. On a real day-to-day, how often can the owner of a PV plant get benefit of ramp prediction? There are many parties involved in the site behavior: PPA, market agent, DNO, control sensor, PPC.
Yeah, so it's a really good question. Well, how often it really depends on also the site. But so now what we are actually trying currently is there are commercial providers for forecasts, and power plant operators and direct marketers are buying these forecasts already. So we are currently working with such a commercial provider, which includes our forecasts, our irradiance forecast into their own PV production forecast. So basically what the operator or direct marketer will get, they are not interested in the irradiance. It's just what they want is they want to get the time series of the PV production itself. And so now our idea is to work with them so that they will introduce this data directly into their PV production forecast, so that the direct marketers have this data continuously available. So they buy it anyways. And yeah, we will see whether or not it will have an advantage. I probably can tell you something in 2 or 3 years. So we just started their pilot project.
Okay, perfect. Well, thank you. Looking forward to the long view in a couple of years.
There's
Yep.
one caveat there. It's PV centric. So on CSP,
Oh,
it's not so much happening right now. Yeah.
oh, okay. Sorry, I thought you already finished. Okay, well, thank you so much, Bijan, for that. Could you stop sharing your slide so we can see everyone bigger? Okay, perfect. So now we're going to move on to the last part of the webinar, which is a round of Q&A. We do have a couple of questions ready for our speakers. However, at any time, please feel free to use the Q&A box for the questions that you might have. So Alex, we're going to go back to you. And going back to your presentation. So does the collector have to be completely defocused, or is it sufficient to reduce the irradiation only partially?
In our case, it's sufficient to reduce it only partially. So you don't need to drive it completely out of the focus. And there's also benefit if you just reduce the focus partially, because then yeah, of course the disturbance in the plant operation gets smaller. So there's yeah, a lot of benefits with this. So what we just need is a temperature signal which is big enough, but this is also the case if you're just reducing, for example, 20% of the irradiance, then we saw that there's still enough signal for this method.
Okay, perfect. You also mentioned the paper that's going to be published in a couple of weeks regarding your findings and your results. How can the participants access that paper? How can we get information with it? Do we go to a certain site, or is there any way that we can get this information?
So the paper hopefully could be published in Solar Energy in the journal, and it will be open access. So yeah, everybody can access it. So you don't need to pay for it. Yeah.
Okay, perfect. All right, we'll keep an eye on it. Thank you so much. Matthias, so a question for you. What are the future development directions for data-driven heliostat models?
So the future directions would be that, yeah, right now we mainly tested all of the data-driven models separately. So, for example, the receiver model and the heliostat field models were tested separately. And already this summer, we started to include both control approaches into one overall control infrastructure, which allows the autonomous control of the whole CSP plant, including the heliostat field and also the receiver. So we are hoping that, yeah, with this autonomous control, we make the CSP also attractive for smaller plants. So by yeah, making it autonomous.
Okay, well, thank you for that, Matthias. We have a question from Jens. I think it's for Bijan, because this is about the last presentation. So Bijan, what are the energy for computing versus higher forecasted irradiance? Do you track energy demand of LLM training as well?
I'm not sure if I got the question correctly. So
Sure. So it says, what are the energy for computing versus higher forecasted irradiance? Do you track energy demand of LLM training as well?
the energy demand for training the models.
Jens, could you, yes, thanks for that. Yes,
Um,
she's referring to that.
Well, I suppose the energy demand for training the model is quite large, but I did not track it. In inference, it's not, but I still don't get the, I don't have specific quantities and we do not track it, but I'm not sure
Okay. Well, Jens, if that's your question, if you were looking for something a bit more specific, you could specify it a little bit more, your question, that would be great. So next question, thank you for that, Bijan, goes to Rafal. So Rafal, do you have any ideas on how to make feature identification better?
So, okay, yes, we have seen that roughly 60% are detected, or features are detected and identified correctly, and have a gap of basically 25% of features which we are losing to identification. And there are two possibilities. First one would be to optimize the flight path, because right now what we are doing is we fly with the drone, record a video, and basically create a point cloud of the field. And then we match this with the available field data from the operator. And by optimizing the flight path, we could have more significant features like edges from the field and so on, which would make the matching better and also the identification better. This is the first case. And then, of course, also the second would be to use better hardware, because right now we are using a relatively simple drone. We have RTK, but I think it was not really activated for this flight. So we have a lot of noise in camera pose. And of course, using a more accurate camera pose would result in a better, better identification here. So these two opportunities.
Okay, well, thank you very much. Matthias, going back to you. In which ways do beam-based heliostat characterization methods offer advantages over alternative characterization techniques?
Yes, so the beam characterization based heliostat characterization, so basically the training of the heliostat models based on target images, has the advantage that this calibration procedure can be fully optimized, and compared to other characterization techniques like deflectometry or photogrammetry, it comes with minimal effort. So we can do one measurement to train both the alignment model and the flux prediction model of the heliostats.
Okay, thank you very much. We have one last question. So if anyone has any questions remaining, it's now or never before we go to final remarks from our speakers. So my last question is for Bijan. How can we actually make probabilistic forecasts from the samples? Oh, you're on mute.
Yes,
Important, important fact.
So yeah, you can generate multiple samples per lead time. So there are different scenarios. And then of course you need the distribution. So let's say you have 8 different scenarios, and you say our forecasts or these scenarios are distributed with a certain type of distribution. Then we can then of course calculate for then normally what we would do is we would use the downstream task, for example, to get from the images irradiance. So we have then 4 different irradiance values. Then we can put the distribution over it, and then we can calculate the quantiles, basically identify different quantiles considering this given distribution for the forecast.
Okay, perfect. Well, thank you so much, Bijan, for that last questions. We do not have any more questions pending, so we're going to go on to final remarks. Alex, is there anything you would like to say before we end this webinar?
Yeah, first of all, thank you for your intention. And if you're interested in the procedure I presented or one of my colleagues, then please feel free to contact us. If you're receiving the slides, then I think we all have included our contact details. So yeah, I would be happy to answer more questions and get in contact with you. Thank you.
Thank you. Thank you, Alex. Yes, I did see all of your emails around the different presentations. So exactly, any questions you might have, you will receive the presentations and the recording in a couple of days. Matthias, any final remarks you would like to share?
Yes, thank you everyone for your attendance. And yeah, as I was only able to give a short overview over all the topics we are working on. There are some references in the slides regarding publications where you can read more about the details of the different approaches and also about the results. And if there are still questions, there are also my contact details. Thank you.
Okay, thank you, Matthias. So there's more to come. Perfect. So Rafael, do you have any questions? Oh, sorry, any questions, any final remarks?
Yes, so I would like to thank again to the audience for attending today's session and for the attention. And yeah, we are always open for discussion or cooperation. So if there's anything, you can reach out to me. The contact details are on the slides. Yep. Thanks again, and yeah, have a nice afternoon.
All right. Well, thank you, Rafael, for that. Bijan, thank you for your presentation. Any final remarks before we leave?
Yeah, I would just also just say thank you to the audience for listening. And I thought a little bit about the question from Jens. So I think the answer would be scalability. So yeah, you're right. Training the model costs a lot of energy. However, you probably can, or we think you can train a model once and then use it on different power plants. And in inference, the energy demand is not as high, but still high. But then it depends how large is the power plant, if it's useful. But we never looked into it, so I cannot give you a quantitative analysis. But I think the solution here is scalability.
Okay, Jen says thank you. So I think that was the that was the right answer. All right. Well, everyone, thank you for attending today. Thank you for your questions. And thank you to our great speakers from DLR. Thank you so much for going through these findings and these results. I know that there's much more to see and that we had little time, but as you said, you all have your contact emails available, and we hope to see everyone very soon in any of our other webinars. So thank you so much for joining. And as Rafael said, we hope you have a great day.